Okay, so let's look at some general techniques then of solving ordinary differential equations, and then we'll apply these to a model like the one we've just been looking at. So we'll look at some practical examples of how you can use these techniques. And next year in the top-up degree course, that's when you'll be using these models to this technique rather to look at some models. Okay. Well, let's start off with some fairly straightforward ones. Is that a differential equation? Right. Because? Yep. Yep. No, it's got one independent variable. Yeah. And what is that independent variable? No, that's the dependent variable, x. So the one underneath, we're differentiating, it's like the differential of y with respect to x. So we're changing x and seeing what happens to y. So it's the dx bit, the underneath bit, that's the independent variable. So if we look at it, I've got my two variables, my independent and my dependent variable here, okay? So it's a differential equation. I've got to try and solve it and end up with y equals something. That's another way of writing the same thing, remember? Y prime could represent the differential. In fact, we might decide to make it absolutely clear that we know what the independent variable is. We might write y prime x equals x squared y, and that's saying x is the independent variable. So that's a nice way to do it. Okay? So if the dependent variable y and the independent variable x are multiplied or divided, we can solve by the technique called separation of variables. Okay? So if you see something like this example here, you're going to use a method of separation of variables. I've spent a bit of time introducing what an ordinary differential equation is and whether or not it's first order, we mentioned, or second order, it's got the second differential in. Because the way you choose to solve an ordinary differential equation is often determined by what type it is. So you need to know what type it is and then you know what to do, okay? So that's how we use separation of variables if we've got something multiplied or divided. The y and x, the dependent variables, are multiplied or divided. For example, this one, you can't use the method of separation of variables because they're not multiplied and divided. They're added. I'd have to use a different technique to solve an equation like that. Okay? But for now, we're going to start off by looking at examples only where they're multiplied together or divided. So let's look at this one. There it is. dy by dx equals x squared y. And we're going to solve by separation of variables. And what we need is to have to hand, or in our minds, that table of standard integrals, because we're going to use integration to do this. So get yourself to hand the table of standard integrals. Okay, so let's go then. So what we do literally is separate the variables. We do what it says on the tin. We get all the parts involving x on one side, so that's the x squared and the dx, and we get all the bits involving y on the other side. That's what we mean by separate the variables. So what we do is we effectively multiply both sides by this dx term, even though really the dx doesn't mean divide by dx. We shift the dx over there, so we say dy equals x squared y dy. So I've shifted the dx. So I've shifted the dx over to the right hand side. And then I shift the y on the right hand side to the left by dividing. So 1 over y dy equals x squared dx. Now I've separated the variables. Now I integrate both sides. I integrate 1 over y with respect to y. And I integrate x squared with respect to x. So by separating the variables, it means I can now integrate both sides. So that's what I do. The integral of 1 over y is log y, the natural log of y. And the integral of x squared is x cubed over 3 plus c. So there's this constant of integration. So we end up with that. Now what we do is we say, there's my solution. Log y equals x cubed over 3 plus c. And this is called an implicit solution, which means that we've solved it, but it's not reading at the moment y equals something. Log y equals this. So it's not in the form that we want it. We would quite like it to read y, which is the dependent variable, which is some sort of, has an independent variable x. So we'd like to write yx, y, which is dependent on x, equals something. So we need to do something to do that. So this is a solution, but we don't often leave it like that. I get rid of the log y by finding exponential e to the, if you remember. So e to the log y equals e to the x cubed over 3 plus e to the c. So we say, from here we can say e to the log y equals e to the x cubed over 3 plus e to the c. It does. I've just put the intermediate step in, yeah, because it's like they're opposite functions, that actually ends up being y. Yeah, they cancel each other out. So, yes. Yes, you do. Like x square rooting gets rid of the square. Yeah. E to the x cubed over 3. Whoops. Yeah. Yes. So they're actually both constants. So actually what we do is we say, let's define something else. Let's let another constant k equal e to the c or something. So we can write k instead of e to the c, but it's just a constant. So we could do that. So now we have a more explicit form of the function. Okay? And we can do something, as we'll see later on, we can do something with this to make it look a bit more like a function we're used to seeing. Okay? But for now, I want to look at the technique, and we'll perhaps come to that later on today and finish that off. Yeah, we'll do that then. So let's finish that there.